Good morning to all of you. A very warm welcome on the third day of the training program. I request Bhavin sir to carry forward the session on hands-on session on device development for the IoT. Bhavin sir, now the audience is yours only.
So, hello everyone. Am I audible to you?
Yes, sir.
Okay. So,
Audible.
good morning everyone. So, our today's session is mostly on hands-on. But before we start our hands-on, I just wanted to explain you that which kind of tool we are using, what is our setup. So, I will start with our steps, our workbook format. Which is we are providing with our setup. So that you can understand what exactly we are doing, how we are doing, which utility we are using for cloud services, IoT services, which protocol we are using. So I will start with some basic idea that what we are using, and then after we will start the hands-on session. Okay. So first, let me share the screen. So I think you guys can see a folder named IoT Lab V3, correct? So in this folder you can see there are many folders, and we are providing some chapters like chapter 1 to 20. Different chapters are there. So uh, initially I will start with chapter 1. Not I won't go with the different setup. Like, let me just stop the presentation. Screen 2. Uh, For some reason, I'm facing error for sharing the document. Just give me a minute. So I think you guys can see a document, correct?
Yes, sir. Yes, sir.
Okay. Okay. So this is our index of a workbook that we are providing with our IoT setup. So initially, the chapter one will be introduction to IoT that we already done yesterday. Then after there is a second chapter is about OpenApp, a tool. OpenApp is a open home automation bus which provide our main IoT services, using which we can use cloud, or you can we can use remotely access our devices. Everything is possible using OpenApp services. And third chapter is how to set up OpenApp. Then after we will introduce the gateway. In our case, the gateway is Raspberry Pi. So how to set up OpenApp service on our Raspberry Pi? That will be chapter 4 and chapter 3. Then after our introduction to our kits, which is chapter 5. Then after we are using a separate board, which is we named as a M4 baseboard. So that kit will be used to interface different sensors and GPR based peripherals. Then comes the Arduino software, because as I told you that uh, Node MCU can be used because it supports Wi-Fi. So in our case, we are using Node MCU. Similar to Node MCU, there is another kit which is called WireNode. So we are using WireNode kit, and for that we are using ID, Arduino ID. Then in the ninth chapter, we are using another library, or I can say ecosystem, which is MBED ecosystem. So that ecosystem basically provide a whole setup. Uh, Let me show you. So here, so Embed is basically developed by ARM systems. So ARM systems, they are using this whole ecosystem specifically for IoT. So as you can see here, Embed gives you free open source IoT operating system with networking and security built in. So basically, we are using the libraries so that we can, which is much more optimized, and we can provide a better solution for students to learn how IoT works. So this is also a very good platform if anyone wants to start, because here you can see there are many boards, many kits are supported. As you can see, these are the kits supported by ARM architecture, or I can say this Embed platform. So you can, if someone is starting their own IoT solution, so they can refer this website. So we are using their ecosystem specifically for the Ethernet based examples. Then comes the Eclipse ID. Basically, instead of using Kale, we are using open source ID, so that the which is very much configured specifically for our kids. So this is the ID. Then after we are in our setup, we are using a router, because there are multiple Ethernet connection, and if we want to use the instead of using switch, because router can be used for multiple devices same at the same time, we can provide internet to the router. So our system will be internet enabled, and we can access our device from anywhere using the using this setup. And from chapter 12, all other chapters are basically examples. So our first chapter 12 is serial based example. In serial based example, we are we are uh, giving some examples like ADC. ADC is nothing but analog to digital conversion, and we can how we can monitor data. First example shows how we can monitor the data. Second example is also same. If there is a device which have like temperature sensor, we have to monitor the what is the temperature and what should be the threshold value. Then how to monitor it. So this is the second example, like how to temperature sensor reads the data, and we can monitor it on our cloud, or can say our browser in our mobile phones devices. Third is like controlling the devices from remotely. So for that purpose, we are using a simple GPR based example, which is LED. Fourth will be relay. Fifth is buzzer, which is also same. We are controlling the device. Then from the sixth, suppose in industry they are using motors like induction motor, step, some servo motors, and some these kind of motors they are using. So instead of using industrial motors and everything, every component, industry component, so to just for explanation purpose or introduction purpose, we are using simple DC motor, and in the last example, we are using stepper motor. So this whole these all examples, the chapter 12 is specifically using serial gateway. Means we are communicating with our gateway using serial protocol. And in our case, we are using UART for serial communication. And this same example, each and every example which is given in the chapter 12 can be performed using different protocol like Ethernet. You can even use Wi-Fi. You can even use Bluetooth. But to explain each and every protocol, we are using in chapter 13 we are using Ethernet gateway. I mean we are sending data through Ethernet to our gateway so that we can control or monitor our devices. Example will be same, like as you can see the first example is ADC, second example is temperature sensor, third is LED, fourth is relay, fifth is buzzer, sixth is DC motor, and seventh is stepper motor. So this kind of uh, setup can be done using the Ethernet and also serially. So in serially we are showing how the device which don't have Ethernet facility or internet facility, still it can communicate to the gateway, and we can remotely access to these kind of devices. Same way, the devices which have internet facility, or we can say Ethernet or Wi-Fi Bluetooth facility. So this kind of device also can access. This kind of device can also be remotely accessed or monitored. So these are two chapters, chapter 12 and chapter 13. In the chapter 14, we are using Ethernet based protocol and we are interfacing some sensors. Right now, in this session, I will demonstrate some of these sensors, not all of these, because there are a lot of sensors available in this chapter. So, like there is first is read click sensor. So as you can see here, read click. Okay, read click. So basically, read is nothing but a magnetic switch. When we are interfacing a magnetic switch to microcontroller, so basically it will work as a simple GPR based application. Like whenever the magnet or avail comes into the proximity of read switch, that switch will toggle. Like if it is off, then it will be on. So this kind of switches can be used for security purpose. Suppose you can use this kind of switch in the doors or window. So if it is open, then you will get the notification, or you can trigger some task, like if the switch is open, yeah, or if switch is closed, then our door is open, then you can start a fan or light if you are using it inside your home. Or suppose if you want to use for security purpose, then you can start some notification, like you will get message or email notification, or you can uh, for higher purpose, you can even use camera. Like if the door is open, you can start the camera and start recording what exactly happening. You will get the image, who is on the door, like who opened the door. So this kind of application can be done using simple read sensor. The second is vibration sensor. Vibration sensor basically used in industry, like in transportation, when they are transporting some kind of liquid or some kind of device which should not be moving, or which should not be vibrate. So using the vibration sensor, we can detect if there is a vibration, then we can take some necessary action. The same vibration sensor can be used in motor. Like uh, if you guys are aware of, in industry they are using different type of motor, and each and every motor has their life cycle. So suppose let's take there is a induction motor, and the life cycle is nearly 3 years or 5 years. So till 3 year or 5 year, you will, when the motor is running, you will get a specific kind of vibration that generates by the motor. We will read the specific that pulse, and we can note down or create database. So when the vibration value change, we can compare our previous data. You can see that vibration is changing, so there is some problem with the motor. So we can use this kind of vibration sensor in this kind of setup. Okay. Then the third one is water sensor, which normally detects water. Suppose there is some liquid is leaking, then using this kind of sensor we can detect that if the liquid is leaking or something like that. Then comes the moisture sensor. So moisture sensor is nothing but a soil moisture sensor. So in soil moisture sensor, we can detect the moisture of the soil. So this sensor can be used in agricultural area. So uh, the instead of pouring water each and every area of the farm, so we can set up multiple sensor, this kind of sensor in the whole farm, and we can manage, we can monitor the area where the what is the moisture value, how we can change, we can provide water accordingly the moisture value, so we can save water. Okay, so this is one of the example of soil moisture sensor. Then comes the PIR motion detection. So this is also the device, I can say sensor, that can be used in home automation for security purpose, as well as we can use this device in industry. Like it may possible that in industry there are some area which in which the machinery is so heavy, or we can say is more dangerous. So human intervention is prohibited. So suppose someone is going there without informing or without taking proper care. So this kind of sensor detects the motion and suddenly stop the machine, so that that some disaster can be stopped. And in the home, we can use for security purpose, like if motion is detected, so that we can take some action. So uh, this kind of action can be taken using the PIR motion sensor. Then comes the dust sensor. So if you guys are aware of, dust sensor basically used in medical application. When they, if we consider ICU, so that area must be clean. So dust sensor basically detects the particles available in the air. So using this reading, we can check that the area is clean or not. So this medical application is one of the application of dust sensor. Then comes the industry. If you are guys aware of our hard drive that we are using in our computer, so that for to manufacture that hard drive, the environment should be clean. There shouldn't be any particle in the air. So using this kind of sensor, we can monitor the area, and if there is a particles or there is a dust, so that we can take some action. Okay. Then comes the touch key. So touch key is nothing but a simple switch, but it is capacitive based touch key, just like our mobile phone screen. So suppose uh, you have a vending machine, which there are multiple products in that machine, so there are multiple switches are there. So if you want to make a log, how many products are sell, or which product is sell in multiple, or I can say, so that we can monitor how many data, how many products are sell, or we can take action accordingly. Like uh, suppose this switch is pressed, the specific action will be taken, or you will get the notification like this key is pressed, and you have allocated this switch for the particular product. Like suppose the vending machine is for the you can say all the Coca-Cola products, Coke products. So you can see that multiple products, different type of products, which products is selling more, which is selling less. So you can plan accordingly using this kind of sensor also. Then comes the ultrasonic uh, sensor. Ultrasonic sensor basically reads the distance. So it basically used in the self-driving or some kind small remotely monitoring cars or something like that. So using this kind of sensor, we can read the distance. We can detect there is an object from at this distance. So this kind of sensor can be used for detecting the distance. Then comes the 10 DOF. 10 DOF means 10 degree of freedom. Basically, the 10 DOF, it is a multiple sensor which comes in a single IC. That is why it is called 10 DOF. The First 3 DOF is accelerometer, second 3 DOF is gyrometer, third 3 DOF is magnetometer, and one DOF is temperature and pressure sensor. So using this kind of sensor, uh, actually this kind of sensor used in quadcopter, so that quad motion of the quadcopter, in which direction it is flying, in which direction it will take turn. So this kind of data can be remotely monitored using this kind of sensor. Then comes the sunlight sensor. So sunlight sensor is also important because it can be used in medical application, like uh, they detect the UV and infrared and visible light using this sensor. We can uh, because sometimes some medicines require some specific lighting. If you consider our simple medicine like eye dropper, then it requires specific temperature and the lightning condition. So this kind of sensor can be used to detect the lightning in a specific area. Then comes the simple temperature and humidity sensor. It can be used in home and industry also. Then we have created some cases using fingerprint sensor and RFID sensor. Like using fingerprint sensor, we can fingerprint and RFID sensor, we can create automatic attendance system in colleges, in school, in the company also. So whenever the person is employees or a student is entering, then they can use fingerprint to enter the his or her data, and the last, after some of the time, it will create a log, and log will be sent to the professor, or you can say our if it is an industry, then it can be sent to um, the manager, that who is uh, who is absent and who is not, and so this kind of log can be created using this kind of sensors. So we are also providing the case studies using these two sensors. Then comes the services. So basically, if you guys have tried IoT, then using like Blinky or ThinkSpace or some other services, so you want able to customize it according to your application. The open app that we are using, it is open source utility, so you can customize accordingly your application. So in our chapter 15, we are using services which can be used which can be used in in a way that uh, like triggering service, or you can take some action. Suppose this there are multiple things, there are multiple embedded device in the single IoT ecosystem. So if there is some action taken on one of the node, one of the thing, one of the embedded system, then accordingly some task will be executed on another node. So this kind of thing can be possible using the OpenApp services. Then after, the second example is like, suppose you are using some ADC, or so you can say our temperature sensor. So you have set the temperature threshold value like 25 degree or 30 degree. So the temperature is above the threshold, like 31 degree or 30 point something degree. So a specific action will be taken. Like it will inform you, you will get the notification. As I showed you yesterday in video, that the on the door that person is there for the Wi-Fi setup. They are asking for the Wi-Fi information, and suddenly the notification went to that person on their in his phone, and he can take action accordingly. So this kind of application can be done using the OpenApp service. The same way, here you can see that in the second example we are sending mail. Even you can send Twitter message. You can even send a normal message. As well, you can set like in a such a way that you can get notification on Facebook also, because we are using a service which provide uh, which which provide many more interfaces. So this can be used for triggering service like this kind of example. Then comes the wireless protocol. We have already talked about serial protocol and Ethernet protocol. In the chapter 16 we are using wireless protocol. The one is Bluetooth. So basically, we are using Bluetooth to read some data wirelessly using Bluetooth to our gateway, so that the data will be directly received via Bluetooth. Then after and that Bluetooth data will be translated and sent to the cloud. So this is how our gateway works. Then comes the Wi-Fi based embedded device, which is in our case is Wireless. So it will read the data from temperature and humidity, and it will send the data using Wi-Fi to our gateway, and then the data will be sent to our cloud so that we can see the data. And as I told you earlier, this is our chapter 17, which is basically explain how we can use database. So in database, uh, we are using in a way like suppose uh, at your home someone is your home, you are not actually you are not inside the home, outside the home, like somewhere else, and some action is taken at your home. So you will get a log inside your Google Calendar. So you will see that this kind of action is taken at home, or if it is office, then you can see that this kind of action is taken at the office. You will get the notification inside the calendar. At the same time, suppose this kind of action is taken and it is not necessarily required. So what you can do, you can create an event inside the Google Calendar. Like suppose the LED, someone started the AC or light or fan, which is not required. Then you can create an event. If there is there is nobody in the office, then the specific after specific time, the AC or light or fan, whatever it is, whatever appliances it is, it will be turned off. So using the Google Calendar, it will automatically turn it off using this kind of database facility. Then comes the database facility that we are using is InfluxDB. So using InfluxDB, we can store data in our IoT gateway. So our IoT gateway also consists of a database service like InfluxDB, and the data will be sent uh, to our database server, and that data can be used to visualize using the Grafana service. Grafana is another utility which used for visualizing the data which is stored in the database. So using Grafana and the InfluxDB, we can visualize what kind of data we receive. Suppose you are using at your home there is a solar panel setup. So what is the reading we had, and you can create graph using Grafana. How much voltage is generated. So this kind of facility can be used. And the last one is the very fun part, which is called MapDB. The name is very odd, but the thing is, it provides very good service. Like suppose you have set up this IoT at your home, and suddenly the light is off, so whole system will be turned off. Then what will happen when the light comes? It will start from the beginning, or it should resume from where it was when the light was off. So using MapDB, what it will do that when suddenly light is off or device is turned off, it will store the current status of whole system, and when the light comes back, it will restore the status, and we can directly resume where it was stopped. So this kind of setup is actually this kind of database, this kind of method very useful when we are using at our home or even in industry, because as you know that the production is going on and suddenly light goes off, then this kind of action can be taken to restore the whole data so that the process can be resumed from where it is stopped. So this is the database examples that we are providing with our setup. Then comes the voice control. Actually, voice control here you can see Amazon Alexa Echo Dot, but with OpenHAB services you can use Apple HomeKit because the same as Amazon Echo Dot, Apple has also developed this kind of speaker, or you can say Siri based of system. So you can control your home appliances using the Apple application. Same way, we can use Google Assistants to control our devices. So in our example, we are using here Amazon Echo Dot. At the same time, I have also developed application currently using Google Assistants. We can control these same devices. Like this same example can be run using Amazon Google Assistants. I will demonstrate you this example today. So this is the voice control based example. Then comes the personal cloud. So as I told you that OpenAI is a can say open source utility. So many people are using that OpenApp service. So let me show you the OpenApp website. So as you can see, there are more than 2000 things are supported on OpenApp, and there are many other companies like Bosch and IBM. They are using this service to set up their own OpenApp service. So what will happen when we are using cloud? So basically, OpenApp also provide their own cloud service. But the thing is, suppose you are using, let's say, IBM Unix. So you are using their service. Suddenly, for the maintenance purpose, they are shutting down their server. Then your whole system will be turned off. You won't able to use your IoT services, correct? For this, for that purpose, what OpenApp provided, they are also providing their own cloud service. And for maintenance purpose, they can also turn off the services so our setup can be stopped. But at the same time, that cloud services that OpenApp provides, they have already provided the source code. So using the source code, we can create our own cloud on Google Cloud or on AWS, Amazon Cloud. So we can implement our OpenApp Cloud on this kind of services. Either you can use Amazon, Google, or Paperspace. There are so many options are there. So you can implement the OpenApp Cloud and connect that OpenApp Cloud to our IoT gateway. So you can have your own cloud. You won't have any problem. Uh, uh, Regarding the access or maintenance issue there, because of that the service is stopped. So something like that can be solved using your personal cloud platform. So we are also providing how to set up your personal OpenApp cloud. And the last is our case studies. So case studies, as I already told you, fingerprint sensor based, RFID sensor based case studies. Then comes the most important part. If you guys are in the previous video, in the previous session, I have shown you a video in home automation that how the device is discovered and automatically take some actions. So this kind of thing is possible using Zigbee network. So in our third case study, what we are doing, we have created a network, mesh network of Zigbee using 4 to 5 Zigbee modules. And what will happen if suppose all 5 Zigbee modules are configured for the same network. Suppose one of the node is going outside that network. So whenever that node comes back to the network, say it will automatically get connected. And after that connection, you can trigger some action. Like suppose this Zigbee modules came back to the network. So accordingly, you can take some action, just like in that video, home automation video. So that kind of application we created using the Zigbee network, Zigbee module. We have also created a case study using Zigbee module. Then after the we have started developing, like as you can see that IoT is much more popular and now the AI is getting popular. So basically IoT and AI, they both are mainly used for the automation purpose. So it can be used in industry. You can consider industry or home. Basically, to make it simple, they are using IoT and the AI. So even they both are separate thing, but we can combine it using some methods. Suppose, suppose you say that weather service. Currently, you can see that that can predict data from 2 days to 10 day after up to the 10 day. I mean 10 days, correct? So you can predict the data using predict the weather, that what will be the tomorrow's weather, what will be after 10 days. So this is possible because of the database, the data they have collected from previous 5 years or 10 years, I don't know, 15 years. So using the data that they can predict the tomorrow's weather, or using this method, using this methodology, I can say, what we have created some application. Like suppose you have data of each and every hour of tomorrow to yesterday, or you can say a whole year. So what will happen? We can use that data and we can train a model so that we can predict the temperature after an hour, okay, after 2 hours, or after whole day, what will be the temperature. So using this kind of system, we can implement in our IoT setup. Like machine, using the machine learning, we can detect the decide the temperature. Like what will be the temperature for tomorrow, or what will be temperature after an hour, and we can take action accordingly that temperature. Suppose, yeah, right, it is a summer. It, think of it like it is summer environment, and there is temperatures in the morning. Temperature is low around 30 degree to 35, and then in the afternoon you will see the temperature is going up to 45 degree. So the temperature is changing, and accordingly that data the machine will train, and it will take action accordingly. Like if it is afternoon, then we can set, like we can turn on AC, we can turn on fan, or we can uh, close the blinds, or we can shutters, close the doors. It will, this kind of actions can be taken automatically accordingly the train model. So this is also possible using AI plus IoT. So this kind of application can be done. And the last one is deep learning based application. Basically, deep learning is much more like image related learning. So we are considering uh, two type of cases. Like suppose you are using in on public area. Like suppose you want to count that how many people are coming or going outside the shop. So you can check what is the peak hour, how many customers are coming. So you want to count something like that. Then you just have to set up a camera, and you can see that the people coming inside the shop, people going outside the shop. You can count the value of that those person, and you can create a database accordingly, and you can take some action. The same way, if there is a production unit in the company, like they are producing bottles or cans, you can take any such item. So what will happen when the device is created, like when the product is created? First, it will be scanned. If there is a error, there is a fault in the product. So if there is if there is a fault, then the machine will take some action, like removing that product from the line, so that it won't get into the final selling area. So this kind of action can be taken using deep learning. Like Suppose you have created you have trained a model for the you can what can say anomaly detection. So this kind of action can be taken using this kind of deep learning setup, and the data will be sent to our remotely accessible network. So as per the action, we can take some measures. So suppose like anomaly detection is increasing, error is increasing, so we can check our machines that if there is a problem with the machine because of that we are producing some bad products, so this kind of action can be taken. And using this is how we can use AI with our IoT setup. So this is the whole setup that we are providing in our IoT solution. And I will, instead of starting with chapter 1, I will start with the OpenApp service, which is chapter 2. So what is OpenHab? I will start with the chapter 2. Then I will directly explain you the kits that we are using for the demonstration purpose, and what is the ecosystem that we are using, like Eclipse ID and everything. I will demonstrate. I will explain you all the software stuffs, and then after I will start with the hands-on. So this is chapter 1, chapter 2. Introduction to OpenApp. So as I told you, OpenApp is nothing but a home automation bus which is open source software, which is basically made from Eclipse PAHO or Eclipse Home Smart Home Service, and which supports many different platforms. As you can see on the web browser, I can show you like released. So in the download section, you can see this many different uh, platform OpenApp supports, like Linux. You can use Raspberry Pi or even your PC. There is a Windows options also here. So you can use Windows PC also, Mac OS also. Raspberry, there is a Pine embedded kit also. And if you guys are aware of Docker, then you can use Docker also. So it is very popular uh, service which is available in the IoT field. So you can start learning what is OpenApp, and you can implement on your own as at the same time. But the thing is, OpenApp is mainly divided into uh, two parts, which is runtime and designer. But the thing is, the runtime service can be managed automatically using the OpenApp core and OpenApp based libraries. So main part that we have to configure, or I can say we have to customize, which is OpenApp designer part. So OpenApp designer part contains three sub part, and that is uh, let me show you this item repository. Then comes the sitemap, and then after it will be rules. Rules is not shown here, but there are three parts that we have to consider to use OpenApp. The first one is item. So item is nothing but you can say in our IoT, Internet of Things. Things means embedded device, correct? Same way in OpenApp language, the items means our physical embedded device. It is called items in the language of OpenApp. Okay. So whenever we are using a specific device, like our relay example, consider relay example, ADC example, or LID example. So we have to create a physical. We already have physical device, but we have to connect that physical device to the OpenApp using the item service. So we have to configure item. That is one part for the designer purpose. The second part is sitemap. So whatever physical device we have connected to the item direct item file, we have to visualize on our web page. We have to create a virtual part that can be used using the sitemap area. So this main part, so using this two files, you can monitor the data, you can use the IoT application, use this kind of setup. But there is one more part which is called rules. So in rules, basically we are designing or we are assigning a specific rules. Like suppose you want to take some actions. If the value is down, then you want to take some action. If value is up, then you want to take some action. If the data is not coming, you want to take some action. So these kind of things can be created in the rules file. So you can trigger some services like this kind of application that is in the rule file. So this is the very basic, very simple overview that I'm giving you of the OpenApp. I will demonstrate, I will show you how the OpenApp works when we start our hands-on. So that is chapter 2. Then chapter 3 and chapter 4 was how to set up our OpenApp service on our Raspberry Pi. So we are also providing, if suppose you have this setup, you can use this you can follow this document, you can create your own IoT application. Then comes the overview of our kit. So if I open this, the first one is our Cortex M3 based kit, which is LPC 1768. So you can see. So this is just a document for what kind of feature available on the kit and how many different interfacing hardware is peripherals are there on the kit. So I'm just going to show you. This is the kit, and I think if I'm sharing my stop the presentation, so I think the camera. Can you see the camera output?
Yes, sir.
Okay, so I think you can see the kit, correct? Hello, can you see the kit?
Yes, sir. Yes, sir.
Okay, yeah. Good. So basically, the kit is, as you can see here, this is the kit.
Sir, can you go a little slow,
Yeah,
sir?
I'm bringing it to.
We don't have the kit, so we need to take down a couple of notes also.
Okay, for that, I will give you the document.
Okay, okay.
Just a minute, ma'am. Just a minute. Actually, I got a call. Just give me 5 minutes. So I'm just showing you what kind of peripherals available on this kit. So as you can see, this is the main CPU, which is LPC 1768. Okay, and if we come down to this area, so as you can see, this is the power connector. Then after here, it is a USB B type of connector. As you can see, this is the USB B cable, which is basically used in printer and other devices. The same connector can be used on this kit. Then comes the UART interfacing connector. I will explain each and every part after just showing showing this kit. Then there is a CAN connector. This is GPIO connector. Here, this is the LCD connector. You can interface LCD on this connector, and this is ADC connector, and this is the potentiometer which we can use to control the ADC output. And here you can see that there is a micro SD card connector. The same time, here you can see there is a USB connector, so you can interface. You can interface. You can what can say pen drive or hard drive on this kit also. You just and this is also. So am I not audible? Because in the chat box I'm getting messages like my voice is not clear.
Fine, sir, fine.
Sorry.
Sir, voice is clear, absolutely clear, sir.
Okay, thank you. So image is not clear because we are using just webcam, and actually I have set the resolution to 720p. Still, if you are not getting clear image, then actually I am not able to give you any. I mean, I won't provide any solution. Okay, but I can. There is one way I can show you. So these are the features, and these are the peripherals available on this kit. But there is one way I can show you the all the features. Okay, so the window select screen. So I think right now you guys able to see the kit, correct? You guys are able to see the document. So this is the kit, and these are the peripherals. So here, this is the part. This is the CPU. The center part is CPU. Then comes the this CPU consists of many features. Like let's go for the features. As you can see, this is the Cortex M3-based CPU, which is 32-bit CPU. Its maximum frequency is 100 megahertz. It has the 500 KB of flash memory. Then after 16 KB of RAM. Then inside the chip there is Ethernet facility, GPIO facility, UART facility, CAN facility. CAN can be used in industry also, in our automobiles also. So there is also I2C SPI facility which can be used for interfacing sensors. Right now, I think maybe some of you guys not able to understand what exactly what kind of protocols are there. So I will explain each and every protocol that we will use in our IoT setup. There is also DMA, direct memory access facility available on this microcontroller. USB is also there, as I already shown you. And there is a very special interface which is called JTAG connector for the debugging. So basically, when we create program like if we are running a Python code, we can execute program step by step. Like we can debug our program. The same way we can use hardware debugging feature which is available on this screen. So we can check if there is a fault. We can check which function is taking too much time, or we can optimize our program accordingly our requirement. So these kind of things can be possible using the debugging feature, hardware debugging feature. So this is also using these all features available on this microcontroller, we have created different peripherals with different connectors. So those all connectors are, as you can see in this kit, these are the connectors that we have created, which the features available on the microcontroller. So let-
How do we program it, sir?
just a minute. First, let me explain the features, and then after I will show you how to program it. And
So one more thing I wanted to ask, is this the kit that you're going to use throughout the demonstration, or
yeah,
is some other kit going to be used?
there will be two kits that we will going to use. This one is the first kit that I will start with the hands-on, and then after I will switch to the Cortex M4 kit. That I will also explain the details of this kit.
Okay.
This kit.
Okay.
Yeah. So
So we are not using Node MCU or any other thing like that, no?
we are actually not Node MCU. We are using just a minute. It is similar to Node MCU. There is another microcontroller. Let me show you. So I think you guys can see, correct? So this is another microcontroller which is battery operated, and there is Wi-Fi also available on this microcontroller. And
Okay.
as you can see, there are three different connectors. This one is battery connector, and these are GPIO connectors and SPI I2C connector, and you can use even UART also. So instead of
Okay.
using non-MCU, you can use this kind of device. It requires
Right.
less space, so you can go for it. Even you can use Node MCU also.
Okay. No, the reason why I asked, sir, is because from at my workplace we have Node MCU, so I could have had bought it, and we could have had done it. I could have had done it simultaneously when you do it. But that is okay. We don't have that, the board that you're talking about.
But you, even though you can perform this practical on Node MCU also,
Acha, okay.
the method will be same. The change is only protocol. In our RT solution, we are showing the same example, but you can change the protocol. Like we are using serial, Ethernet, or you can say Bluetooth, Wi-Fi. We are using services, but the example that things that we are using for demonstrating this example, we are using the
Ah,
same peripherals like LED relay or some sensors. So just
okay.
changing part is only protocol that we are using. The same way
Okay.
you can use the same method, you can use same example, and you can use Node MCU also using same procedure. Procedure will be same. There won't be any issue, and you can run the examples.
Okay, sir.
So just a minute. So the document. So this is the kit, and you can see on the here we will start with the right upper corner. It is some power adapter connector, which is barrel connector, 9-volt supply required to power on this kit. Then below that connector there is a USB connector. So basically the question that I got, like how to flash this kit, correct? So the method is method is using this USB connector. We can connect a USB A to B cable to our PC, and using that cable and the utility, Flash Magic utility. Let me show you Flash Magic utility. Okay, this is the utility using which we can flash our kit. So as you can see in the first step, we have to select which kit we are using. Then after on which connector the kit is connected. Then after what is the baud rate, at at what speed it is transferring the data. Then after the oscillator frequency, each and every microprocessor or microcontroller, it requires external signal. Using that signal, it can work, like it will generate the clock. So we are using here 12 megahertz crystal. Using that crystal, so this is the crystal. Using this crystal, we are generating a signal, and the clock is generated using the crystal, and the CPU is working. In the second step, we have to decide what area of the flash we have to clear. Like we can erase all the flash, or you can erase only part that will be used for our program. Then in the third step, whatever the file that we have compiled, that compiled file will be, that will be selected in the third step, that will be flashed in the fifth step. So when I press the start key, it will start flashing the program, and the program will be flashed on this device, and the program will run. Okay, so this is the flashing method. Then below that USB connector, there is another connector which is DB9 connector. That DB9 connector is basically used for UART communication. So UART is nothing but simple serial communication, universal asynchronous receive transmit in protocol. So this is the first protocol that is developed for microcontroller for debugging purpose, even for communication purpose. After UART, the technology changed, the CPU frequency got increased, the performance increased. So different serial protocols came into picture, like I2C. So on the left side there is a 4-pin connector here. That 4-pin connector is I2C connector. As you can see on the image, there is I2C is written over here. Okay, so after I2C is invented, still the requirement of the communication between two devices is faster. So there another protocol is developed, which is called SPI. So below I2C interface, there is the SPI connector. So using SPI protocol, we can communicate in Mbps speed. So this is the 3 serial protocol. Then below this USB connector, sorry, this is UART connector, and below the UART connector there is a CAN interface connector. So we are using the same, sorry. We are using the same connector type, DB9 connector for CAN interface. CAN interface. So CAN interface is nothing but basically used for controlled area network. So in automobile, as you can see that if the accident occur, it will suddenly open the airbag. It will execute some task which is very fast, because accidents happen very the time is very short. So in the short time we have to take some action. So for that, the same way like our Ethernet network, our IP network, the same way CAN network is working. It can it is continuously communicating each and every device available in the network, and whenever some action should be taken, that action can be directed to specific device, and that device will execute the task. Like if the accident occur, it should open the airbag, right? So this kind of action is taken using this kind of protocol like CAN. So basically mainly CAN protocol is used in automobile. Then comes the right side down down corner, below corner. Then you can see that there is a GPIO connector. GPIO is general purpose input output connectors, pins. Each and every microcontroller have GPIO interface, like input output interface. Suppose there is a sensor which only requires to send signal in digital format, like the voltage will be high or voltage will be low. Voltage will be high considered as a 1 and low considered as a 0. So this kind of signal will be sent using GPIO interface instead of using this another protocol. We are using simple GPIO protocol. So every GPIO based peripheral that we provide uh, will be connected on this connector. Uh, okay, and we and on the left side of that connector there is LCD connector. So this kit supports different peripherals, different protocols. So there are LCDs available in the market which uses I2C and SPI interfacing protocol. So using this protocol, we have created some examples using which we can interface touchscreen LCD on this connector. So this is the 34-pin LCD connector, and on the left side there is an ADC connector. So when we start our hands-on, so first example will be how to execute. First example is ADC based example. So how to read the data of ADC. ADC is nothing but analog to digital conversion. So when we provide analog signal, like when we provide voltage signal, uh, this kit works on 0 to 3.3 voltage. So suppose we are providing voltage between 0 to 3.3 volt. So what will happen? The ADC, analog to digital conversion, will convert that analog value, that voltage value, to a digital number. So suppose the voltage is 0, then the digital value will be 0. Suppose the voltage is 1.5, then the value will be around 2000 or 1500. Then when the voltage value is around 3.3 volt, then the value will be 4000. So how that value will be decided depends upon the ADC technology. There are different type of ADC available in the market, like 8-bit ADC, 10-bit ADC, 12-bit ADC. So this microcontroller supports 12-bit ADC. So 12-bit means you can count that 2 raised to 12. What will be the number? That number will be divided into 0 to 3.3 volt. Okay, so this is how that value will be decided. So on which voltage which value will be shown. So this is ADC feature available on this kit, and there are sensors like soil moisture sensor which sends data in ADC format. There is water sensor which also sends data in ADC format. There are sensors like signal detection, like suppose there is a voice speaker like mic sensor. So if there is small sound, it will generate some voltage. So that voltage will be converted into digital format, and the data will be displayed on our display on our web page, or I can say the IoT system. So ADC is also important part in IoT. Then above that ADC connector, there is a micro SD card connector. So this kit also supports SPI interface, SPI protocol. So there is a library available which uses SPI protocol to interface micro SD card to this kit. And above that there is a USB host connector, as you can see here, USB host. So a USB host is nothing but like the kit will work as a host, and you can connect device like pen drive or hard drive to this kit. So basically, when we are using Windows operating system or Linux operating system, a specific file system is required. For Windows, there is NTFS file system, okay, and Linux there is extended file system. The same way, if you want to interface pen drive or hard drive, mass storage device, any mass storage device to this kind of kit, you must require a library, or you can say software, so that it can read data from the sectors of that mass storage device. And for microcontroller, it is called FATFS or ChainFS. There are multiple different type of library available in the market. So we are using FATFS. So using that FATFS, because FAT format supported by the pen drive. So we are using that library to interface pen drive to this kit. Then comes the above that there is an Ethernet connector. So this kit also support Ethernet. So we are basically using Ethernet for creating web server. If we are not using for internet IoT, then we can create our own web server using this connector, using this microcontroller. And we are using for Internet of Things. So Ethernet based data will be sent through this connector. So these are the basic feature available on this kit. And as you can see on the upper part in the center, there is a black connector. So that black connector is used for JTAG, I mean debugging purpose. So this is the hardware debugging feature available on this microcontroller that can be used using this connector. So these are the basic feature of this microcontroller. And each and every connector detail and each and every peripheral detail given in this document. So as you can see, this is the architecture of the LPC1768 microcontroller. Then comes the hardware details. As you can see, these are the hardware block diagram of our LPC1768 kit. And from this point, you can see there are different connectors available, and each and every connector details will be explained in very thoroughly here. As you can see, this is the power connector. As you can see, 9-volt supplies is required. The CPU frequency is this. Crystal oscillator is this. Operating temperature is this. So using this document, you can even understand what kind of features available on this kit, how it is used, and each and everything is given in this document. So the first is 9-volt supply. There is a power connector. What kind of connector is that? How it is connected? Then the USB connector, flashing connector. There is USB B that I already explained you. Then comes the UART connector. So as I already told you that this DB9 connector here, as you can see. Then comes the CAN connector. So this is a document. You can refer this document to understand how the kit works and what are the features available on this kit. Okay, and all the details available in this document for this kit.
So are you showing some written material? We cannot see that. I can see only the board.
Sorry.
I can see only the board. Are you showing some written material?
So you weren't able. You didn't see the document. Actually, I have presented the document. Was it visible or not?
Yeah, ma'am. Maybe because of you have pinned the screen, pinned to screen. That's why you were just
No,
you were
actually,
just showing the
I
kit.
haven't.
Yes, sir. Yes, sir. We were able to see that. We were able to see the document, but maybe the ma'am who is having this query, she have pinned your screen.
Okay, okay.
Yeah, yeah, I had pinned a screen.
Yes,
Okay,
that's
okay,
right.
okay.
Please,
Okay,
so please.
I got it. So actually, right now I have stopped the presentation, so nothing is visible. But let me show it again. So
Yes,
the
sir.
second part is chapter 6 and chapter 5. So the second CPU that we are going to use in this session, which is Cortex M3, Cortex M4, and let me share the window. So this is the another kit that we are going to use in our uh, IoT session, and I will focus mainly on this kit because this kit is much more powerful and it has much more features. So basically the kit looks like this. So this is the kit. Let me remove this. So this is the kit that we are going to use for this session, and this is Cortex M4 based kit. Actually, as you can see, this is a separate module which is connected on this baseboard. Okay, so I will first explain this part. Then after I will explain the below part. What are the features available on this kit and everything. Okay, so first let's start with the main CPU kit, main CPU board. So as you can see on the screen, this is the picture of the kit, and in the center you can see. I think you guys able to see, correct, the document?
Yes, yes.
Okay, yeah. So in the center you can see the STM32F407 microcontroller. This microcontroller supports many features compared to that Cortex M3 based LPC1768. So this kit also supports onboard debugging that can be possible using the upper connector, which is CN1 connector. So this is the connector using which we can flash the program in this kit. Even we can debug the program using the same connector. So for this kit we won't require external hardware. The hardware is already available on this microcontroller kit. As you can see, there is a small IC below that connector which is used for the debugging purpose. And as you can see, here we are using only 8 MHz crystal to operate this kit compared to that LPC1768 we are using 12 MHz crystal. So using 8 MHz crystal, this kit inside there is a whole clock mechanism. Using the 8 MHz crystal, it can generate up to 240 MHz frequency. And currently, whenever we are running the program, it works at 168 MHz frequency. Okay, so this is the clock area, and as you can see on both the side, there are different connectors are there, numbers are there, correct? So those numbers are basically nothing but a a connector, pin wire connector, and all the peripherals, all the pins available on these microcontrollers are connected on this external pins. And using these pins, we can connect our own hardware, or you can say our own peripherals to run the example. And there are some onboard peripherals are also. So as you can see, there is a blue color switch. That blue color switch is user switch. You can use for your own application. And on the right side, there are 4 LEDs. Right now, the LED is not on, or I can turn it on without using program. So there are 4 LEDs are there on board, and in the center part there is a small IC. That small IC is nothing but an accelerometer module, and on the left side there is a black color switch, which is a reset switch, using which we can reset the program. And below that switches there is a small IC, black color IC, which is nothing but audio decoder. As you can see, there is a black small connector. There is a small black connector here. That black connector is audio jack connector, and on the right side there is a small connector CN5. That connector will be used to interface mass storage device, just like LPC1768. And even you can use devices like keyboard and mouse. You can interface keyboard and mouse on this kit also. So for that, this is the connector, CN5 connector will be used. And on the right side of the CN5 connector, there is a small IC, black color IC, that is mic. So on this kit, you can use mic also. You can play audio also using the audio jack connector. So these kind of features available on this module. Okay, so and here are all the details available on this kit, and I will just go through it so that you can understand the features. As you can see, there is a power LED, there is a SWD connector which is for debugging, there is a current measurement is possible using this jumper. This is the CPU, there is a user button, there are, as I told you, there are 4 LEDs, there is a green, blue LED, there is red LED, orange LED, or is there is a green LED for the detection purpose. Suppose you are connecting a master device or any keyboard and mouse hardware, then that LED will turn on for indication purpose. It is there. There is red LED is also for indication purpose. Then here you can see the reset button. As I already told you, reset button is there. It works at 3 volt power supply. But basically, when we connect this kit to our computer, so that connector from the connector you will get 5 volt supply from the USB. So the 5 volt will be converted to 3 volt on this onboard power supply management circuitry, and the kit operates at 3 volt supply. Okay, so these are the feature available on this kit. Then comes the baseboard that we are using here. So this is the block diagram of baseboard. So our kit will be mounted on this connector, these 2 connector, and below these 2 connector there are some semiconductors are there. So using those semiconductor, we have features like Ethernet, UART. Okay, there is the SD card connect, micro SD card connector also there. You can even interface camera. So let me show you. So here in this section, there are, you can see as a there are 2 connectors are there, correct? This is the micro SD card connector and this is the camera connector. Here you can see that this is the camera connector. So you can interface camera on this microcontroller too. Then after you can see there are different connectors are there. So those connectors will be on the left side. In the document you can see that on the left side there is a power socket. So it also required 9 volt supply. And that 9 volt, so below the 9 volt connector, there is a LCD connector. So it also supports I2C and SPI protocol, so you can interface LCD also. So you can see the camera output directly on LCD. There is a GPIO connector, the same as our LPC 1768. I2C SPI connectors are also there. CAN interface is also available on this kit. But as you can see on the left side, we are using multiple UART connectors. UART 6, there is a DP9 UART 6 connector. There is a USB B type UART 4 connector. So we are providing multiple different type of connectors on this kit. Same way as I already told you that we can use ZigBee in our IoT solutions. So you can directly interface ZigBee on this kit, which is not possible in Cortex M3 based kit. Then comes the on the right side below connector on corner, below corner, there is a EDU bus connector. That is specifically designed connector, as you can see on this kit. So this is the connector, which includes many features like ADC, interrupt, I2C, SPI, UART, PWM. So these all features are available on this single connector. So suppose you have sensor which requires different peripheral, different protocol. So that can be used on this connector because we have some sensor that uses this kind of connector. So on this kit, we can use many features which is not available on our LPC 176 kit. So that is the only reason I am showing you. I will show more example on this kit. Okay, so this is the basic introduction of this kit that we will going to use in our IoT setup. Okay, this is the image of that microcontroller kit, and after that, as you can see, there are different connectors available on this kit, and all the details of these microcontrollers are given here. Which kind of, how many pins are there for connector, and what are the details of that microcontroller connectors. So each and every details are provided in this document. You can refer this document and you can make your own application. So let's go back to the index. That was chapter 6, and after chapter 7, chapter 7 is nothing but the Arduino IDE installation steps. Then after chapter 8 is introduction to wire node kit. So that meme asked me about the Node MCU. So let me show you this kit. This is nothing but kind of Node MCU because it is using ESP8266 just like Node MCU, but it required less area. It can operate on battery because there is a battery connector. There is a status LED, and flashing is also very easy, which is also provided in this document. And I think there is no image of that kit in this document. So this is the wire node. This is the wire node, and you can see the features available on this kit. There is a function key, there is a reset key, there is a micro USB connector using which we can flash the program. There is a ESP, as I told you, ESP8266 microcontroller is there. And here you can see there are 3 different connectors on the back side. One connector supports UART I2C and GPIO connector, and the second connector is analog I2C and another GPIO connector, and this is the battery holder. So you can use this device as mobile device in your home area or even in your industry. So you can wirelessly send data to the IoT server directly. Okay, so this is the our wire node, which is more like Node MCU. Then comes the Embed project that I already talked about. And now I will just give you a brief idea of Eclipse IDE. So here we are using Eclipse IDE. So this is the Eclipse IDE. It is starting. So this is the when we start Eclipse IDE or any other IDE, it requires a specific area for working on application. So when we use Turbo C, so in Turbo C it creates a simple folder, and it will put all the files inside that folder if even the user is changed. Correct. So instead of making that that kind of instead of working this way, what the feature that Eclipse provide, it creates a workspace. Like here you can see there is a STM32F4 workspace. There are different workspace for LPC 1768. There is also a workspace named Embed 1768. So what it does, it creates a separate directory for each and every different architecture of the CPU. So here I will just open it using the STM32F4 workspace. So what the workspace will be used for creating your own projects. So each and every projects will be displayed on that particular area, and that can be imported or exported into the files. So whenever you want to directly use the your uh, project, you can directly import it, or you can also export the project. So the Eclipse is starting. Will take a little bit time. So this is the Eclipse ID, and as you can see, there are some of the projects are there, and you can see the interface. So this is the Eclipse ID that we are using for compiling, or you can say the application creation area. You can consider this ID as a in which in this environment we are making our examples. So on the left side, you can see the Project Explorer window. So in the Project Explorer window, you will see there are multiple projects are there. So each and every project will be separated using separate directory. As you can see, the first directory is free RTOS multitasking example. Second directory is Mutex. Third is Q. Then fourth is semaphore. Then after there is also template is also there. So basically, template Eclipse ID comes without any configuration. So first we have to configure the Eclipse ID so that we can use for particular microcontroller. So the template, which includes multiple projects files, as you can see, there are multiple projects files are there in this template. Okay, so beside that window, there is editor window. This is the editor window which can be used for modifying or creating the source file or header file. Then on the below there is a console window. Here console window, when you compile the program, if there is an error or the successful building message will be displayed on this console window. So these are the basic feature that is we are using in Eclipse. And there is also a debug window. So debug is whole new interface. When we can debug our microcontroller kit or our program, so it will start this different window, and here we can execute our program step by step. So each and every step can be executed one by one using here. These keys are currently disabled because we are not debugging any program. So these are the step. You can step into, step over, and you can step return. So this kind of key, using this kind of key, we can step by step execute our program. And below that, you will see the at which location our current program is. So this is the location where we can see our current program. On the right side of the editor window, here you can see the registers which is currently being used in microcontroller, and you can see the value, which value is inside that particular register. You can even see the memory of that register. You can see the assembly language coding of that program. So there are multiple features available for debugging also. So that because of single utility with multiple features, we are using Eclipse ID. So this is very brief introduction of Eclipse ID, and as you can see, this is our project. In our project, we include multiple files. So you can see there are folders called driver. In the driver, you can see BSP. BSP are the drivers that we provide with this microcontroller. So as you can see, there is a LCD driver, timer, UART. There is I2C driver, LCD calibration driver. There is accelerometer driver. There is a CAN driver, camera driver, audio driver, ADC driver, USB HID. There are multiple drivers are there in this setup, and in the source directory, it will be the main file in which you will use the application code. So this is the main file, and this is the main program that will be used to execute, that will be executed first in our coding. So this is the brief introduction of this kit. So let's go back to the index, and here I will not show you how to compile the program and everything because it will take our time. It will consume our time. So I will directly use the compiled program and flash that program into the into our microcontroller, and we will execute the program. Okay, so I think we should take a break, and we will start after the break, if it is fine with you. Hello. So we will start the hands-on session in the our second session. Okay. So we will start with the Cortex.
Okay, sir.
Okay, we will start with the Cortex M3 kit and some serial gateway-based example. Okay. Then we will start with the Ethernet-based example. So this is how we will go through, and I will also make it more interactive because after compiling one program to switching to another program, it will take a little bit of time because flashing and changing the files and everything. So it is possible that you might get bored. So I will try to make it as much as possible that it will be interactive. Okay. So we will start 2 o'clock our hands-on session. Okay.
Okay, sir.
Okay, so I'm
Okay, sir.
session.
Okay, sure, sir.
Yeah.
So all the participants, this is lunch break up to 2 p.m. and we will again start our session at 2 p.m. Thank you all.